Hello, in this talk I'm going to tell you about our paper titled The Complexity of Gradient Descent, CLS equals PPAD intersection PLS, which is co-authored with John Fernley and Rahul Savani from the University of Liverpool and Paul Goldberg from the University of Oxford. So let me start off by just mentioning some interesting computational problems. The first one is Nash. Given a game in normal form, compute any mixed Nash equilibrium of the game. Next, we have a very famous problem, factoring. Given a number in binary representation, compute any prime factor of that number. After that, we have Brouwer. Given a continuous function f from the unit cube to itself, compute any fixed point of that function. What is a fixed point? It's a point x, such that f of x equals x, namely the point remains fixed if you apply f. Then we have a similar problem, contraction. Given a contraction function from the unit hypercube to itself, compute the unique fixed point of that function. And finally, we have the problem pure congestion, which is given a congestion game, compute any pure Nash equilibrium of the game. And if you don't know what a congestion game is, don't worry, it's not important for the talk. So let me now ask this question. What do these problems have in common? And the first thing they have in common is that they're all quite interesting and natural. But from a technical standpoint, all of these problems are so-called NP total search problems, also known as TF&P problems. And this is because they have two crucial properties. The first one is that they're total. For any instance of the problem, there necessarily exists a solution. And the second property is that they lie in NP in the sense that it's easy to verify solutions. If I give you a candidate solution, you can verify in polynomial time if it is indeed a valid solution or not. Let's quickly go over these problems to see why they are total. So Nash is total by Nash's theorem, which tells you that any such game has at least one mixed Nash equilibrium. Factoring, is total because any number has a decomposition into prime factors. In particular, it has a prime factor. Brouwer is total by the famous Brouwer fixed point theorem, which tells you precisely that any such function has at least a fixed point. Contraction is based on another fixed point theorem, Banach's fixed point theorem, which tells you that a contracting function has a unique fixed point. And finally, it's well known in the study of congestion games that every congestion game has at least one pure Nash equilibrium. So all of these problems are TF&P problems, but they also have something else in common, these five problems, which is that we don't know how to solve them in polynomial time. People have tried to come up with polynomial time algorithms and have failed. So it's generally believed that the problems are hard to solve. And of course, as theoretical computer scientists, we would like to provide some evidence for that, explain why we don't have polynomial time algorithms for these problems. And so a natural follow-up question is, can any of these problems be NP hard? Or more generally, can any TF&P problem be NP hard? And perhaps surprisingly, the answer here is no, not unless something very surprising happens, namely that co-NP equals NP. So unless this very surprising thing happens, no, we don't expect NP hardness to be a way to show hardness in this case. Let's take a closer look at this. So the class TF&P, defined by Megiddo and Papadimitriou 91, contains all total NP search problems. So there are three things to note here. First of all, we're talking about search problems. So we're looking for an actual solution, not for a yes-no answer. It's not a decision problem, it's a search problem. Then the problem should lie in NP, namely given any candidate solution, there should be a polynomial time algorithm that checks whether this is indeed a solution or not. And finally, the crucial property of totality. For any instance, it is guaranteed that there will exist at least one solution. So if a problem has these three properties, then it is a TF&P problem. TF&P is interesting because it contains all of these natural problems, but also because it lies between P and NP, or rather the search versions of these two classes. And so studying problems in this class is very interesting, even if you just care about P and NP. So I mentioned that a lot of problems are hard, or are thought of being, we think they're hard in TF&P. So how can we provide evidence for that? Showing that the problem is NP hard is not an option, because that would imply that NP equals conp. Let me briefly sketch why that is the case. So assume that you have a polynomial time reduction from 3SAT to Nash. Now, because Nash is total and solutions can be verified efficiently, that immediately implies that you can have certificates, small certificates, for unsatisfiable 3SAT formulas. In other words, 3SAT lies in co-NP. And as a result, you get that NP equals co-NP. So the summary here is, unless NP equals co-NP, NP hardness is not the way forward. The next best thing is to maybe we can show that some problem in TF&P is as hard as any other problem in TF&P. That would provide some evidence of hardness. But even that we don't believe is possible because of how general TF&P is as a class. It's not believed that it has any complete problems at all. So that doesn't seem like a good option either. So what can we do? What Pavel Dimitriou proposed around 30 years ago is to investigate the landscape inside TF&P. Try to understand how problems inside TF&P relate to each other, which ones are harder, which ones are easier. Try to organize them into subclasses of TF&P and understand how these subclasses relate to each other. So over the years, various subclasses have been defined. Let me mention a few of them. The first one I want to mention is PPP. You can think of PPP as containing all TF&P problems for which totality can be shown by using the pigeonhole principle. In other words, you can prove that every instance has at least one solution by using the pigeonhole principle. Next, we have the class PPA, which contains all problems where totality follows from the parity argument. An example of a parity argument is the handshaking lemma, for example. So if your problem that you care about, if you can prove that it always has a solution by using some kind of parity argument in the proof, then it's likely that your problem will lie in PPA. PPA also has a nice characterization using a famous topological theorem, which is called the Borsuk-Ulam theorem. So you can also think of PPA as containing all TF&P problems where totality follows from the Borsuk-Ulam theorem. Next, we have a very successful class, PLS. PLS contains all TF&P problems where totality follows from some kind of a local search argument. And the pure congestion problem that I mentioned on the first slide is complete for PLS. Another PLS complete problem is local max cut, which is find a cut in a graph that is maximal up to taking one vertex from one side of the cut to the other one. So up to these local changes, it's optimal. That problem is PLS complete. And PLS has been very successful in capturing the complexity of local search optimization problems. So it's a very successful class. And the last class I want to mention is PPAD. PPAD contains all TF&P problems where totality follows from some kind of a directed graph argument. I don't want to explain what that is, it's not important here. You can think of PPAD as just containing all problems where existence of a solution can be proved by using Brouwer's fixed point theorem. In other words, the Brouwer problem that I mentioned earlier is PPAD complete. And famously, the Nash problem is PPAD complete. And since then, many other problems from game theory, and not only from game theory, have been proved to be PPAD complete. So it's also a very successful class. So we have these two classes that are very successful. But why do we think that proving that a problem is PPAD complete or PLS complete, why do we think of this as being evidence of hardness? And I think there are at least three reasons that I can give you. The first one is that many seemingly hard problems lie in PPAD or in PLS, which means that if you were to prove that some PPAD complete problem is actually easy, that would imply that all of these problems are also easy, which seems a bit unlikely. Another reason is that we have very nice separations, oracle separations between these classes, and also between these classes and P. So that's one kind of evidence that these classes are not easy. And the final thing is that it has been shown that these classes are hard under cryptographic assumptions, meaning that if you believe that some kind of cryptographic primitive exists, then PPAD cannot be equal to P, PLS cannot be equal to P. And there are various results with various different cryptographic primitives. This is another piece of evidence. Let's go back to a picture, zoomed in into PPAD and PLS. So what Daskalakis and Papadomitriou noticed around 10 years ago is that there are a lot of interesting natural problems that lie both in PPAD and in PLS. In other words, they lie in this intersection. And let me give some examples. The contraction problem that we saw, the problem of computing a mixed Nash equilibrium of congestion game as opposed to pure Nash equilibrium, which is PLS complete. The problem of solving a P-matrix linear complementarity problem, PLCP, which is some kind of generalization of linear programming. The problem of computing a fixed point given by Tarski's fixed point theorem. The problem of solving simple stochastic games, etc. So a lot of interesting natural problems lying in this intersection. And because it is believed that PPAD and PLS are incomparable, as evidenced also by oracle separations, that means that these problems, they cannot be PPAD complete. They cannot be PLS complete, because that would imply a collapse or a containment. So they have to be something else. So could they be PPAD intersection PLS complete? Daskalakis and Papadomitriou argued that this seems unlikely because PPAD intersection PLS seems like a very unnatural class. And let me explain why. So consider a problem A that's PPAD complete and a problem B that's PLS complete. And let's construct the following problem, either solution of A or B, which is defined as given an instance of A and an instance of B, find a solution to one of the two, whichever one you want. In other words, I give you an instance of problem A and an instance of problem B, and I tell you solve one of the two, whichever one you want. I don't care which one, but solve one of the two. So it turns out, and it's not hard to show, that this problem either solution is PPAD intersection PLS complete. If problem A is PPAD complete, if problem B is PLS complete. So let's instantiate that with some specific examples. So let's take that problem A to be Brouwer, which is PPAD complete. So that problem is defined as follows. Given a continuous function f that maps the unit hypercube to itself, the goal is to find a fixed point of the function f, namely a point x such that f of x equals x. Now for technical reasons, we actually consider the approximate version with a precision parameter epsilon. So you ask for a point x such that f of x is epsilon close to x. So this problem is PPAD complete. And for our problem B, we're going to take the PLS complete problem, real local opt. We're given in the input two functions. First, a continuous function p mapping the unit hypercube to the 0-1 interval, and then a function g from the unit hypercube to itself, which, importantly, that function g, it does not have to be continuous. It can be non-continuous. What is the goal of this problem? The goal is to find a local minimum of p with respect to g, namely a point x such that p of g of x is greater or equal to p of x. And intuitively, this just means a point x where if I apply g, I don't get a better point with respect to p. I don't get a point that decreases the potential p. Again, for technical reasons, we have to add this little epsilon. And this problem is known to be PLS complete. So as a result, this problem, either solution Brouwer real local opt, is PPAD intersection PLS complete. Now the problem is that, this problem is not very natural. In fact, it's very unnatural. You're given two completely unrelated instances and have to solve one of the two. How could you relate this to all these natural, interesting problems that we saw earlier. And so, as Kalakis and Papalimitru said, there's a much more natural way to combine Brouwer and real local opt. There's a much more natural way, and that's the problem continuous local opt. Continuous local opt is the same as real local opt, except that now G is required to be continuous as well. Not only P, G also has to be continuous. That's the only difference. So clearly this problem continuous local opt is a special case of real local opt, and as a result it lies in PLS. But it's not too hard to see that it's actually also a special case of Brouwer, because now that the function G is continuous, finding a fixed point of G lies in PPAD, and finding a fixed point of G is enough to solve this problem. It's not too hard to check. So in other words, we have this problem continuous local opt that lies in PPAD and in PLS, and is more natural that all these is much more natural than all these either solution problems. So as Kalakis and Papalimitru said, let's define a class based on this problem, the class CLS, which stands for continuous local search. So let's go back to a picture, zoomed in to just PPAD intersection PLS, which has these weird complete problems, either solution. And we have this new class CLS, defined using the complete problem continuous local opt. And Kalakis and Papalimitru showed that for most of the interesting problems in PPAD intersection PLS, they actually lie in CLS. And so the argument is that CLS is a much more natural class, much more likely to exactly capture the complexity of these interesting problems. So this was the state of the world before our work. And we started our investigation with the following observation, which is about the motivation behind the definition of the classes historically. So if you look at PPAD, the formal definition of PPAD was essentially PPAD is a set of all TF&P problems that can be solved by a path-following algorithm. And it was inspired by the Lemke-Hausen algorithm for Nash. So when I say solved here, I don't mean in polynomial time. I mean that every step of the algorithm can be performed in polynomial time, but there might be a lot of steps. So in a path-following algorithm, every step of taking one step forward on the path can be computed efficiently, but the path might be very long. PLS has a similar definition as a set of all TF&P problems that can be solved by a local search algorithm. Again, every step of the local search algorithm can be performed in polynomial time, but there might be a lot of steps. And CLS now, more recently, can be viewed again as the same thing, but with continuous local search instead of local search. And so we thought to ourselves, let's consider another classical, very important algorithm, which is gradient descent. And let's define a class that we call GD, which contains all TF&P problems that can be solved by gradient descent. And again, doesn't mean in polynomial time by gradient descent, but every step of gradient descent can be done efficiently, and then you don't know how many steps it's going to take. Could take a lot of steps, could take a few steps, you don't know. Now this sounds very good, but when you say something like this, a class of all TF&P problems that can be solved by gradient descent, you have to formalize this somehow. So how do we formalize this? How do you define a problem capturing gradient descent? So the way in which we do this is we take the input to be a continuously differentiable function f from the unit hypercube to the 0, 1 interval, and we're also given a step size eta and a precision epsilon. And if you remember what gradient descent is, gradient descent just repeatedly applies the following update rule. The next iterate, xk plus 1, is obtained from the previous iterate, xk, simply by using this formula, which uses the step size and the gradient of f. And that's it, just repeatedly do that. And so what should be the solutions of our problem capturing gradient descent? It should be any point where gradient descent terminates. But here again, you have to specify what that means. Where does gradient descent terminate? And there are at least two very natural ways to define that. The first one is to say gradient descent terminates when the next iterate, does not improve the value. The next iterate decreases f by most epsilon, not by enough. It's not worth continuing. If you take this point of view, then you obtain a problem that we call GD local search, and it's not too hard to see that this problem lies in CLS. It's a special case of continuous local opt, essentially. So that's one way of interpreting termination, one stopping criterion. There's another one that's very natural, which is to say that gradient descent just terminates when the next iterate is very close to the current one. In other words, x is a solution if the next iterate of gradient descent is epsilon close to x. And if you take that point of view, then you obtain a problem that we call GD fixed point. So we have these two different ways of formalizing this definition of GD, but fortunately it turns out that it doesn't matter which one you pick, you get the same class. So these two problems are polynomial time equivalent, so you can use either of them to define the class. You will get the same class. Let's get back to a picture. That's what it looked like before. And now let's add the new class GD. So the class GD is defined using this problem GD fixed point, for example. And as I mentioned, GD is a subset of CLS. It's a special case. It's not too hard to show also that mixed congestion lies in GD. But what we do is that we study a problem in GD, which we call KKT, which is the problem of finding a stationary point of a continuously differentiable function over a compact domain. And so this problem, it's not hard to see that it can be solved by gradient descent. Finding a stationary point, that's exactly what gradient descent is good at. So we study this problem KKT, and we show that it's not only GD hard, not only CLS hard, but as it turns out, it is PPAD intersection PLS hard. So this problem, which lies at the bottom of the hierarchy, turns out to be as hard as the whole largest class, which means that the three classes actually collapse to a single class. So PPAD intersection PLS is the same as CLS, is the same as GD, and this class has all these complete problems and contains all the interesting natural problems that I mentioned. So this collapse was very surprising, unexpected, because of how unnatural PPAD intersection PLS seemed as a class. And so the consequences are that, as it turns out, PPAD intersection PLS is an interesting class after all. It has interesting complete problems. It has a very nice characterization in terms of continuous local search or even gradient descent, right? PPAD intersection PLS is the class of all TF&P problems that can be solved by gradient descent. And there are also some technical consequences about the robustness of the definition of CLS and GD in terms of dimension, domain, etc. Let me just finish this talk by mentioning some future directions. The first one is that other interesting classes, an interesting class A, an interesting class B, where if you take the intersection, you get some interesting class out of that. Other examples of this phenomenon. And the second future direction is, okay, we know now that PPAD intersection PLS is interesting. We know that it has complete problems that are natural. What about the rest of the problems that lie in PPAD intersection PLS? Which one of them are also PPAD intersection PLS complete? And so I've put some candidates here. Contraction is a candidate, Tarski is a candidate, polynomial KKT is a candidate, the problem of finding a stationary point of a polynomial, and mixed congestion is also a candidate. And actually the two last problems on this list, they've been solved in the sense that they have been proved PPAD intersection PLS complete. So Babichenko and Rubinstein have proved at this very STOC that the problems are PPAD intersection PLS complete by reducing from our GD fixed point problem. The other ones are still open. So thanks a lot for your attention.